This class, chemistry, is a science class, and to start talking about science, we need to understand how science differs from things like philosophy or religion or democracy, right? Science has a different model in which it does things, right? It makes observations, and then from those observations makes kind of rough conclusions and hypotheses after those conclusions. So, for example, here, there's somebody who has a duck in the water, and they think, well, the duck's going to eat bread because it's a duck. And so they try to feed the duck some bread. That's the hypothesis, that the duck's going to eat the bread. But the duck doesn't eat the bread. And so when the duck doesn't eat the bread, they make more observations, make more conclusions, and make a different hypothesis and perform a different experiment based on that hypothesis. Okay? And it's cyclic in nature. Science is cyclic in nature. You have observations, hypotheses, and then there are experiments that are performed, and from those experiments you can have more observations and create more hypotheses. So once you do this over and over and over, you get what are called models. Now, a model, we might call it a theoretical model, because it changes. It can change now and then, and it does change. But the model, the idea behind the model, is simply something that allows us to kind of communicate with somebody else about it. So this up here, these are both models of the atom. This was an early model, and this early model, the top one here, the green one, was called the plum pudding model. And the idea here was that there was an area, a region, kind of like a bowl. This is the region where the atom exists. And then there are spots where larger particulates within the atom, specifically positively charged protons or negatively charged electrons, would kind of roam around. So this is the plum pudding model of the atom. And it answered some questions and allowed people to kind of think of the atom like a bowl of pudding with these different larger components inside, but mostly empty. But it didn't answer all of the questions that we had. It doesn't represent how matter behaves and such. And so you have to kind of redefine the model after a variety of experiments. And so this is kind of a more recent model, this lower one here, where we have a nucleus now that contains the protons, and we've also introduced neutrons, these orange things, whereas the electrons are kind of orbiting on the outside. Now, this is a model that we have, and we'll talk about the ways that this model works and doesn't work, kind of fails, as we move through the chapters here. But in general, we want to keep an idea that all of these kind of models that we provide are only models. And we don't want to say that they are the end-all be-all of everything. It's just kind of the most recent understanding of something. And so there's this nice little video that I'd like to show you here about what, it talks about models. And after we watch it, you could tell me why you think that they made this video. That would be great. So here we go.
You're watching a Nova Science Now video podcast.
All right, so what do you think? Why do you think Nova put together that video?
To broaden our conception of what is really involved at the atomic level.
Okay, very good. Yeah, it teaches us a little bit more about what's at the atomic level. Also, I think there's another thing. Essentially, at the end there, they kind of showed the model of the atom and showed the whole central part. What were they trying to kind of help us recognize by doing that? What were they trying to show us?
The kind of that there's a big space, and that I got that the electron moves more like a mosquito that doesn't have a circular motion around it. It has all this space to roam.
Yeah, good. That's good. Another thing I think that they were trying to do. Did you have one more comment?
No, not really.
Well, another thing that I think that they were trying to show is that it would be kind of difficult for us to conceptualize and visualize an atom if we were really small or if it was really large right in front of us so we could see it better. It wouldn't be something that we could really describe very effectively to our friends simply because it's not something you can see in a single frame, right? So the model that we provide, which is the nucleus with these electrons around it, is a fine model, but it's just a model. It has limitations, and we can't be afraid to kind of break out of the models, whatever they are, whether it be the atom or how atoms behave or molecules behave, whatever it is. You can't be afraid to break out of them when necessary. Okay, so once we gather lots of information and get to the point where we're talking about models and that have developed into a theory, tested explanations for how things occur, we can also reach a level of what we call a scientific law. And in a scientific law, what we're really talking about is eventually an equation, right? So if you have an equation like this one, and this isn't something we're going to talk about or that you have to remember anytime soon, but it shows that the pressure on a system is equal to some constant divided by the volume of that system. And it's an inverse relationship. There's a linear relationship, might say. As one goes down, the other one goes linearly up, right? So, scientific laws generally are related to equations. Okay, now we're going to go through a few different terms that we want to kind of become familiar with, and you probably have heard of some of these terms already, but it's good to remind ourselves. Matter is basically everything. Everything's made of matter. And we give matter the term, kind of a bad definition. It's just anything that has mass, right? So basically everything. Well, maybe not light, or an energy, but basically everything, right? All material is matter. Now mass, the term mass, compared with the term weight, like how much do you weigh, right? We usually say, I lost weight the other day. Well, there's a difference, and we don't stress it a whole lot in this class, but we want to begin to be aware of it. And essentially, that difference between mass and weight is that weight is dependent upon the gravitational pull of the Earth, whereas mass is independent of this. So let's show some examples, and you might have seen this example before. But if I have a scale, and I stand on my scale, and let's say I'm a big guy and I weigh 600 pounds, right? 600 pounds. So if I weigh 600 pounds, the way that this scale works, I put my feet on it, right? And I weigh 600 pounds. It's the spring that's in the scale being squished by my mass, and how much it's squished is related to the gravitational pull of the planet that I'm on, right? That Earth that I'm on, Earth, right? Now, if I wanted to kind of find my mass, I would have not a scale, but I would use what we call a balance. Now on a balance, I would stand on one side here, and I would have a mass, a 600-pound mass, on the other, and this would be balanced if I had a mass of 600 pounds. If we took our scale here, so if this is kind of occurring on the Earth, say this is our Earth here, but if we took it and went to the moon and had a much smaller gravitational pull, smaller body of mass, right? The scale would no longer read 600. Do you happen to know what the difference between what the scale would read? Any ideas? More or less or the same?
Close to 0.
It'd actually be about 100, about 1/6.
Oh, really?
Yeah.
Oh, okay.
I mean, not that you should have known that, but I mean, the gravitational pull of the moon is about 1/6 that of the Earth.
I see.
And so because my spring wouldn't get squished as much because the gravitational pull is less, I would only have a weight of 100 pounds. However, if we wanted to compare our balance on the moon, right, here I am, standing on the moon this time. What do you think? What kind of a mass am I going to need to balance on the moon? Any guesses?
It should be the same 600.
Yeah, that's right. It's going to be the 600. Because on the Earth, the 600 is pulled down a certain amount based on the gravity. Here it's pulled down less, but it's also pulled down on this side less by the moon. So yeah, go ahead.
Well, so what I'm confused with is, or maybe I need clarification, is how did we first establish that my mass is 600 pounds?
That's a good question. And that's right, that we had to find a standard, a national standard. And they have labs that protect these standards very well. And every year there are concerns about, oh, the standard has lost 0.000001 grams. How are we going to control that? And over time, I mean, these masses, which are, I think it's spheres of, I can't remember if it's lead. I can't remember what, no, it's not lead because lead oxide. I can't remember what the spheres are made of, but they're perfect kilograms. And that's what they're trying to, if I remember right. I might be wrong with that. But they initially had masses, they had lengths, right? All these things to kind of measure a standard for everybody else in the world that they could compare against. Nowadays, they've kind of changed how they do that. They want to make it so that anybody in any lab anywhere can make a standard of whether length or mass or energy or whatever it is. For mass, they still haven't figured out a way to do that. But for length and for time, for example, they can measure how long a beam of light will travel for a certain amount of time. So they can allow any lab to create a fixed length if they want to. So it's these standards that they have in the world that all scientists kind of can get access to if they need to in the long run, right? So yeah, go ahead.
Quick question. So with our model that you wrote down there, you first had the person step on a scale.
Yeah.
And they weighed 600 pounds.
Yeah.
And then we switched from the scale to the balance, and we put that 600 pounds in the form of mass. So can we assume that for the Earth, mass can be measured by the scale first, and then it can fluctuate? Then we realize that way the mass is different, but when it's on Earth, it's the same.
That's essentially right. Yeah, that's right. We've made it so that on Earth, our mass and weight are kind of the same. And so it's really not that big of a deal, but the definition of the term weight and mass are different. So in some situations, people much prefer you to use the term mass, right? Because it's a representation of how much material there is as opposed to a force that's related to the gravitational pull. Okay, good. So, some more terms that we want to become familiar with. All right, an atom. Now, this isn't a term that's we're unfamiliar with. We already kind of talked about this a little bit. And our model is protons and neutrons together in a nucleus with electrons around the outside. Are you familiar with that a little bit? Protons and neutrons in the nucleus and electrons on the outside?
Yes.
Okay, great. Excellent. So when we combine atoms, so I'm going to draw a picture here of an atom. Here's one atom with one proton and one electron around the outside. And here's another atom with one proton and one electron around the outside. When atoms get closer together, come close together, they can combine, well, interact with each other and form bonds and create what we call molecules, where now the electron density of both of these atoms is free to, let's move this out of here real quick, is free to interact with both of the nuclei, right? So this here is a molecule, or you might want to call it a compound, right? That's when you take atoms separate and bring them together and you form molecule. And the simplest of molecules or compounds are just a couple atoms, but you can have very, very complex molecules. Like this one here has 6, 7, 8 of the black carbon atoms and 3 oxygen atoms and a variety of hydrogens there, the white ones. All right, so that's a more complex molecule. But you can also have very, very complex molecules like a strand of DNA, right, which can be meters long. So strands of DNA are also molecules, molecular compounds. All right, so molecules or compounds are words that we can use to talk about groups of atoms that have come together to form new entities with different properties. All right, elements. Now, you've probably heard of the periodic table. Let me bring up a picture of the periodic table here for us. Elements are the different Legos, the different building blocks that we have to make everything in the world, right? And this is a table of all those elements, periodic table of elements. And they differ from each other by the number of protons that they have in their nucleus. And the number that each element is given is the number of protons that that atom, that kind of element, has in its nucleus. So if I look at boron here, boron, that 5 there, tells me that in the nucleus of boron there are 5 protons. All right. Argon, here's argon. Can you tell me, can you see how many protons does an atom of argon have?
Can you point out argon?
Right here.
Oh, I see. Okay, 18.
18. Very good. Very good. So the number on that, the top left number there in this periodic table, and sometimes the numbers move around a bit, so you have to kind of recognize what's going on, is the number of protons, positively charged atomic or subatomic particles in the nucleus. And you can see they're in order. 1, 2, 3, 4, 5, 6, right? Ascending order, getting larger, right? So another example here, gold. An atom of gold has 79 protons in its nucleus. All right, excellent. Now, the number of electrons that each atom has is generally going to be, if the atom is not charged, the same as the number of protons. Now let's talk about what that means if the atom is not charged, okay? Let's draw some of our atoms. I'm not going to draw gold with 79 protons, but I'll draw something like carbon. So I'm going to draw an atom of carbon. It has 6 protons. 1, 2, 3, 4, 5, 6. Positive charges. I'm putting a little plus sign on them. If the atom is neutrally charged. Neutrally charged. That means that the same number of positive charges as negative charges. So it's not just 6 protons, but also 6 electrons, and we can draw those as little minus signs, 3, 4, 5, 6. All right? Because it's the same number of protons, 6 positive charges, as electrons, 6 negative charges, then they're equal to each other. There's no charge on this species. So if we know there's no charge on a given atom, I could ask a question, or somebody could say, I have an atom of zinc, right? And here's zinc. I have an atom of zinc, and it doesn't have a charge, so how many electrons must it have? And we know it has 30 protons, so if it doesn't have a charge, how many electrons does it need to have? Well, 30 electrons. That's right. Very good. So, protons are indicated by these numbers, and if there's no charge, then also those numbers indicate the number of electrons. All right, so those are our elements, right? And when we say something is elemental, that means that it's made up of just those elements. So, for example, if I have a gold ring, right? My ring of gold here, typically, or not typically, almost never do you see a gold ring actually just made of gold, because 32 or 24 karat gold is too malleable, too pliable, too easy to bend, so nobody makes it. But let's just pretend that this is all gold, all gold. I could say that this was elemental, right? It's an element. It's just all one atom, one kind of atom, right? There are some other examples like diamonds. Diamonds are all made of carbon. You can have elemental sulfur. You can have elemental oxygen, oxygen gas, right? Doesn't need to be a solid to be an element. It can be a gas too. All right. So our elements can exist by themselves, and when they're by themselves, then they're called elemental or elements. If they're in combinations, what do we call them? If our elements are in different combinations and form new entities, what are those called?
Compound.
Compound. Very good. Compound. Excellent. And another name that I'm going to introduce more fully later is molecule. Molecules.
Okay, that was my next question, was the difference between the two.
Very good. And let's talk a little bit about that difference here as well. Okay? I'm going to draw kind of a diagram here to talk about the different kinds of what we call compounds. All right? If this circle represents all the different kinds of compounds that exist in the universe, all right, amongst these compounds, some would be what we call molecular, or molecules, okay? And the way that we can identify whether a compound is a molecule or molecular is that it's made of non-metals. It's a combination of non-metals. Now, if we look back at our periodic table, we haven't talked about which elements on here are metals and which ones are non-metals. But I'll show you that the metals and the non-metals are almost completely separated by this green staircase here. This green staircase. So the green staircase separates the metals from the non-metals. And I don't know if you can see it well enough here, but once we know that the green staircase separates the metals from the non-metals, then we can look at this side over here. We can see things like nickel, cobalt, iron, all right, zinc, silver, gold. So the left side of the periodic table are our metals, whereas the right side over here are our non-metals. Now, there is one exception over here to the far left, which is hydrogen. Hydrogen is also a non-metal. Is that safe to understand? Is that fair?
Yes. And then how do we, the ones at the base?
All these are also considered metals.
Oh, okay.
And we'll talk more about how the periodic table is designed later, but these ones actually go right here. Can you see my mouse moving around at all or no?
Move it a little bit more. Yeah.
Okay.
Yeah, I can.
See where this green box and this kind of pinkish box down here? These are
Yes.
these are placeholders for these lower inner transition metals, we call them. And we'll make sure we understand them later on. But they're all metals. All right. So, molecular compounds are compounds that are made of non-metals. So, only contain non-metals. And while we're here, we'll introduce a second group of compounds, which are called ionic compounds. So you have molecular compounds and ionic compounds. Ionic compounds are compounds that contain, so if this is our group of ionic compounds, they contain a metal and a non-metal. All right? So if we have a periodic table nearby and somebody asks us, or we want to know whether a compound is a molecular compound or an ionic compound, we can use the periodic table to answer that question. So here's an example. I'll write it down here in the corner so we can still see most of the periodic table. H2O, water. Is that a molecular compound or an ionic compound? Well, it's molecular. That's right, because hydrogen's nonmetal and oxygen's nonmetal. So it's made of nonmetals, so it's a molecular compound. Very good. Let's give you another one here. Sodium chloride. All right. Is it a molecular compound or an ionic compound? Well, we got to find these two. Can you find them?
I can't quite find them. Could you point it out on the
Yeah.
chart?
Sodium over here is number 11. And chlorine,
Okay, metal.
and chlorine is number 17.
Okay, and that's metal too.
Nope, this is to the right of this staircase.
Oh, okay, I could. Yeah, I couldn't see the arrow. Okay.
Okay, all right, yeah.
Right, so that's ionic then.
That's right. Very good. An ionic compound. Excellent. So, now outside of this whole circle that I've drawn, right, of compounds, we have other kinds of materials, and one of those other kinds is just elements, right? Stuff like gold, oxygen gas, nitrogen gas, right? Anything that's elemental. Nickel, right? Only diamond or carbon, right? Okay, so we have compounds broken up into molecular and ionic, and then elements, and that when it's elemental, it's just one kind of atom in that substance. Did you follow that okay?
One kind of atom?
Yeah, one kind of atom. So if I say this is gold, this is a piece of gold, that means the only kind of atom that exists in there are gold atoms.
Right.
So they're
Okay,
all...
So we're talking about it's just an element.
Yeah, just an element. Very good. Okay, excellent. So, the periodic table has these symbols, as you're becoming familiar if you weren't already. And the elemental symbols relate to the names of the elements, and these are just ones that we made up. They're not from on high or anything like that. And these elements combine together into the chemical formulas, which are compounds. So here we have our different elements, and water, H2O. Now, when you see water, when you see H2O, is it clear enough to you, or you have any familiarity with how you can determine how many? So we can hopefully see that this contains hydrogen and oxygen, but can you tell how many hydrogens and how many oxygens this molecule contains?
So the two would indicate two elements bonds of hydrogen.
That's right. 2 atoms of hydrogen and then 1 atom of
atoms.
oxygen. Very good. And in the same way, carbon dioxide here, CO2, 1 atom of carbon for every 2 atoms of oxygen. So our elemental symbols combine into chemical formulas, and those formulas help us know the ratio of the different elements within those compounds or molecules.
So is atom and element, are they synonymous?
Synonymous?
Yes.
Well,
If we say we have an atom of hydrogen, I guess we don't say it's one element of hydrogen, right?
yeah, it doesn't quite fit,
So, okay, I got you.
but
So
you're,
element is denotes what kind of material it is. Atom is the quantity.
the atom
or
is
the-
like the individual one, right? And
Yeah.
the kind of atom is called the element. Is that fair to say?
Yeah.
Yeah, so if I said I have an atom, it has 5 protons in its nucleus, what am I talking about? You would say you're talking about the element boron, right? Or that's an atom of boron. Okay?
Right.
And that's something that we don't stress a whole lot, but it's important. It's very important. But hopefully, we're hoping that it'll kind of distill on you gradually as time goes on.
Okay.
Good. So let's look at some of these other elements that don't have names that are related to, or don't have symbols, sorry, that are related to their English names. You can see that these are kind of the elements that were kind of discovered early on, right? People knew about gold, silver, copper, iron really early on. And that was back when the chief language for the sciences was Latin. Therefore, they still maintain their symbols, which refer to their Latin names. Okay? So, we're not going to be responsible for kind of memorizing any of these, but as we use the periodic table more and more, we'll get familiar with where the elements are and also their names and symbols as well. Okay? So, we talked about compound. We talked about a compound. And we talked about how our compounds are broken up into 2 groups, molecular and ionic, and how elements are different kinds of materials, different class of, a different way of classifying materials. Now, here's some examples of some chemical formulas. Sodium chloride is probably one you've heard of before, NaCl. This is another example of a compound, FePO4, right? There's, thousands, millions of different combinations that we can have for these compounds. FePO4, let's see if you can, give you a little test here. Is FePO4 a molecular or an ionic compound? Try to get the periodic table here so you can see it. What do you think?
Can you enlarge the table a little bit?
Here's the Fe.
And, okay, so we know that's a metal.
Here's the P. And here's
And then,
the oxygen.
yeah, so that's, okay. So that would be a molecular, I already forgot the termination, ionic?
Ionic compound. That's right. Very good. Ionic compound. Very good. So, that's our little review on compounds. And then we have different kinds of reactions, ways that we can kind of draw a chemical and then write an arrow and then draw the products, and this whole thing we call a reaction. A reaction. Okay? Yeah, go ahead.
So I just need a quick review again. The molecular is something that is, the molecular denotes that there's two nonmetals, or there's no metals at all. It's just nonmetals,
That's right.
right?
That's right.
And then the ionic is contains
A metal.
at least a metal and non-metal.
That's right. Very good.
And then is there one that contains just two metals?
There are classes, courses that you take in college where you talk about metallic bonding and what we call inorganic. Well, not inorganic, but that's the name of the class where you talk about that sort of thing. And yes, but this class will generally be talking about only these two types.
Oh, okay, good. Okay.
These two types of compounds, and then we'll also refer to elements as well.
So I know that I'm not going to see any that has two metals being combined.
That's generally the case. That's generally the case. I mean, every time I say that, there's going to be a few exceptions, and we might run into something along the way, but that's generally the case.
Okay.
All right, and you'll also learn that as we grow and understand more in this class, I'll come back to things and say, well, you know what, I wasn't really telling the truth about that. It's actually like this, right? And so I'm kind of gradually leading up to an understanding of how things are, but we can't, don't hold me to these definitions too tight. There'll be a few exceptions along the way, and we'll see them, but these will help us the best way. Kind of like that model changes over time. All right, so let's look at some examples of chemical reactions compared to also what we call physical reactions. Physical reaction. Now, we don't talk a ton about physical reactions in this class, but we talk mostly about chemical reactions. However, we want to be able to differentiate between a chemical and a physical reaction. You'll see questions along the way sometimes about, hey, is this a chemical reaction or a physical reaction? Or what happens when this reaction occurs and it's just a physical reaction? Because we want you to make sure you recognize that sometimes a change doesn't necessarily mean that a chemical reaction has occurred. Okay? Now, you would think that this was kind of clear, and our understanding of it is pretty clear if somebody says a physical change. Now, let's do some examples of a physical change. If I have something like gold, that's elemental gold, and it's solid, and then here's the change that's going to occur. I make it into this, and that little L there means that it's now a liquid. What have I done to that gold? Taking it from solid to liquid, what do we call that?
Well, you melted it.
Melted, that's right. That's a melt. Okay? Now, I haven't changed the way that these elements are interacting with other elements. So this is not a chemical change. This is just a physical change or a physical reaction. All right? A chemical reaction almost always has to deal with more than one kind of element, but here's an example for us. Taking hydrogen atoms, combining with oxygen atoms, right, to form, H2O, water. And now we haven't introduced balanced equations, but you might see, hey, there's two hydrogens on this side. Where'd you get them from? So we'll put a 2 in front of that one to say I got two hydrogen atoms, one oxygen atom. They come together in a new way. So this is not a melt. It's not a freeze or a boil, right? We're not doing a physical change. This is a chemical reaction. Okay? So a chemical reaction will have the products, and here we call these our products, and the left side of the equation or the arrow is our are our reactants. All right. So this chemical reaction is generally easy to identify because the elements are now interacting with each other in a different way, in a way that they were not beforehand. All right. So, there's not a whole lot of physical reactions that can occur. I can take this liquid gold, and if I keep heating it, I'll get, that's a U, and then there's G for gaseous state, right? So this is a liquid state. This is the solid state, right? Solid, melting it to liquid. What do you call it when you go from a liquid to a gas? Any ideas?
I always think of boiling point.
Yeah, very good. That's fine. I'm boiling or evaporating, right? Is that another one? Okay. So, again, I'm not changing the kinds of atoms that these are interacting with. This is still gold atoms interacting with each other, but just in a different phase. Okay?
I have a question.
Yeah.
Can all elements be achieve the three physical states, or do some have limitations?
Yeah. Essentially, yeah. Now, here's a tricky one for you that you might want to think about. Now, this isn't an element, but if you think about something like wood, right? If I have wood and I get it really hot, let's say this is solid wood, and I get it really hot, why don't I ever have liquid wood? And the answer is because when you get this really hot, it begins to react with the oxygen gas that's around. And so you don't get liquid wood, but you get things like carbon dioxide and water being produced when you combine this. Wood is really, C6H12O6, kind of a general chemical formula for what the material is that's in wood. So you won't get this solid becoming a liquid very easily because of the reactivity of the oxygen that's around.
So that becomes a chemical change.
That's a chemical change. That's right. So a lot of your chemicals, or even your elements, you heat them up, but if you don't take care to remove other elements like oxygen or nitrogen or what's in the air and stuff, then you'll get other kinds of chemical reactions occurring simply because of their reactivity. So yes, you can take anything from a solid, right, to a liquid, and then to a gas, provided that you make sure you remove everything else and don't cause them to chemically react. Also, it might take a lot of heat. It might take a lot of heat, but it's possible.
So if each one is an element that by nature that's the lowest, that's the most simplest form, right?
Of that element, of that kind of atom. Mm-hmm.
Right. So then we're ensured that's going to all be a physical state, right?
That's right. That's right.
Whereas wood is already wood is not an element.
That's right. That's right.
Right.
It's kind of an example, and it's an early kind of thing that people were trying to figure out. They would take the wood and they would burn it, and they would have a lot less mass, and so they would say, "Oh, well, I guess we melted away something, and when that happened, that energy that was lost in the form of the fire disappeared. The mass disappeared somehow." They didn't know that they were losing carbon dioxide and some as a gas, and some water as a gas as well. So same type of thing, if you perform a reaction with other things around, you might think, oh, you can't turn it into a gas or a liquid, but it's possible as long as you can prevent the reactions from occurring. Okay, good. So chemical and physical reactions. Our chemical formulas. We talked a little bit about our chemical formulas already, but these chemical formulas, H2O, FePO4, NaCl, H2SO4, from them we can identify the number of different atoms and the different kinds of atoms that are in a given compound. And this becomes very critical, very important for us to be able to look at any compound. So let's look at the H2SO4, for example. We need to be able to look at something like H2SO4. I can see, hopefully really quick, there's three different kinds of elements. I got hydrogen, I got sulfur, and I got oxygen. But we need to be able to make sure we're careful about counting the different numbers of those kinds of elements. And it's usually really straightforward, but we got to be careful. How many hydrogens are we representing here? Two. How many sulfurs? One. And 4 oxygen. Very good. Now, when I put a number in front, 3, we have to recognize, I'm not going to put in parentheses because that's not what you do, but we have to recognize that that 3 is saying that I have 3 of these whole things. Right? So now, how many hydrogens would this statement represent?
6.
6. Very good. And 3 sulfurs and 12 oxygen. Okay, so we call that number in front the coefficient, and the coefficient is telling us how many of these whole units we have. You never want to get tricked into thinking that that is telling us something about just this or maybe a little small segment of it, right? It's telling us I have 3 of those whole segments. Okay? Now, free elements sometimes are not what we call monoatomic. They're diatomic. That means they go around in pairs. So hydrogen, for example, you never just find a single hydrogen atom. It always goes around in pairs as H2. Oxygen, same thing. Elemental oxygen, O2. Elemental nitrogen, N2. Elemental chlorine, Cl2. All right. And sometimes you get even larger. P4 exists, S8, P10, O3. You've heard of the ozone layer. That's O3, 3 atoms of oxygen combined together. Okay. So these are not just, elements are not just single atoms sometimes. Sometimes they go around. These elements go around in what we call molecules because these are groups of elements now. But they're still elements, but they're now groups. And so we can call them molecular elements. It's not all, and it's just kind of a small handful, but it does become critical as well. So, for example, let me write a chemical reaction where we don't want to lose our understanding of what's going on. Here we go. I have this chemical reaction here. I'm combining hydrogen gas with oxygen gas, both elemental, and forming 2 molecules of water. All right. How many hydrogens are represented on the right side of the equation here, Walt? What do you think?
4.
4. Got 4 hydrogens over here. How many oxygens?
2.
2 oxygens. Now, if this equation is balanced, then the number of hydrogens and the number of oxygens should be the same over here. Is it?
No.
How many hydrogens do I have here?
4.
4 hydrogens. How many oxygens?
Oh, I see. I was going to say 4.
But there's only 2, right?
But we have, yeah, I see. We have the plus. If we didn't have the plus.
That's right.
If it was H2O2, then be 4 and 4.
That's right. Very good. But that plus is indicating that there's this chemical plus this chemical. And we're not showing the coefficient there, are we? What is the coefficient there, though?
1.
It's 1. That's right. And we won't, sometimes I'll do it there just to emphasize something, but in general, when it's just 1, we don't put it in there. Very good. So we have a balanced equation. Excellent. And we want to become familiar with looking at both sides of the equation and making sure we know how many of the different kinds of elements exist on either side of the
So
equation.
you lost me a little bit on the diatomic
Okay.
molecule.
Yeah.
So they go in groups of 2,
That's right.
and it's usually all non-metals.
It is.
Right.
Yep, that's right. The only exception there is mercury. But
All mercury's
Yeah.
the exception. Okay.
But you don't have to worry about this too much. This is another thing that's more going to kind of settle on you and you'll understand. But these are fine questions, so go ahead and keep asking.
Well, when I see there at the bottom, O3, right, the ozone,
Uh-huh.
I mean, all the others are even, so I would expect all to be an even number if they're going around in pairs.
Well, I guess it's not only,
In groups of 2, right?
it can be groups of 2, but it doesn't have to be. It can be groups of 3.
Oh, it doesn't.
Yeah.
Oh, I see.
It can be groups of 8. Phosphorus can be found as a group of 4 or a group of 10. So you do have some scenarios where larger clusters of elements or atoms are going around as in their elemental form. In general, these are the major ones that we kind of want to watch out for. Hydrogen, oxygen, nitrogen, fluorine, chlorine, iodine, and bromine. Okay?
Okay.
And they'll usually give us ways to know that we're talking about elemental materials. They'll either write it down for us, so they'll say something like this, F2. Okay? Now, the only thing that we want to make sure we recognize is this is still an element, even though there's 2 fluorines, it's just one element, right? There's just one kind of atom there. Or they'll say something like elemental chlorine. Elemental chlorine. Well, if they're talking about chlorine as an element, then we need to remember that it goes around in Cl2 as Cl2.
Oh, I see.
Okay, good. So, sometimes chemical formulas can be written more than one way. And this isn't, sometimes early students want to say, how's the right way to write the equation? Do you write the carbon first, the oxygen, nitrogen, metals first, non-metals last? How exactly should it be done? For ionic compounds, usually the metals first, and almost always the metals first. But in general, it doesn't matter a whole lot. You'll begin to gather how these elements or these molecules or compounds are written gradually. But we don't need to be concerned if we see, for example, here's one way of writing this element, or this molecule, CO, NH2 with parentheses, and then a 2 there. CO, NH2 in parentheses with the 2 there. So that, let me write that down for us on a piece of paper so we can explore it a little bit. CO, inside parentheses, NH2, and then a 2. And then the compound itself looks like this, and you don't have to worry about this for now, but you might be able to see why the chemical formula was written the way it was by looking at its structure. What we have here is CO, here's our CO, and then we have NH2, but that NH2 is in parentheses, and so we're having 2 NH2 groups. So sometimes, another way to write this chemical formula, which you might see, is CON2H4, right? That's a completely legitimate way to write it. But this helps us. The second one helps us understand the structure a little bit. Now there's other ways that the carbon and oxygen and 2 nitrogens and 4 hydrogens, there's other ways that they can come together to form compounds. This isn't the only way. So it's possible that you see a chemical formula and it can represent more than one kind of molecule. All right. But what we're learning here is with these parentheses, and with that 2 that's outside the parentheses, it's saying we have 2 of these NH2 groups. And so if I wanted to identify the number of carbons, oxygens, nitrogens, and hydrogens in this compound here, let's see. Can we do it? How many carbons do we have?
One.
One carbon. How about oxygens? One. How about nitrogens? Two. One inside, one NH2 in here, but there's 2 of them. So we have 2. And hydrogens?
Four.
4. Very good.
That's kind of tricky, huh?
Yeah, it is a little bit, right? You have this
Because
NH2.
we're talking about the 2 on the hydrogen. That's 2 atoms, right?
Yep.
But then I also heard you say when just a little while ago that you can also say there's 2 molecules.
2 molecules of this material.
Well, if you go back to your on that paper, on that same paper,
Oh, this one here?
somewhere you wrote down F, a different equation, you wrote down F2 or F2.
Uh-huh.
And I thought you referred to that 2 as a molecule.
This F2. Yeah, it can be called molecular.
Oh, okay, so, I see. So you're referring to the whole element.
Yes.
An element, F2 is an element, right?
Right. F2 is an element.
And
That's
you're
right.
You're referring to that as also a molecule?
Yeah, because the word molecular really is referring to how the compound kind of resides, or how the compound interacts with other compounds. And fluorine, the word molecular is kind of like the word modular. Now, I don't know if you know the word modular very well. Probably so, because you've heard of modular homes, right?
Right.
Homes that are kind of one piece and then they can move around as a home, as opposed to lots of boards that come together and make a house, right? Molecular is the same type of thing. So when this compound is molecular, what we're saying is it's 2 fluorines that go around in a little packet and do their chemistry like that. So the word molecular, and that's a good understanding. It's kind of like synonymous with the term modular.
Okay, so it's a compound. I didn't realize it was a compound.
Yeah.
I thought was the F2. I thought was
It is
element.
It is an element. It is an element.
But by itself, right?
It is an element,
I mean, it's
by itself. And on our table here of where it would belong, it's kind of hard to say where it would belong, right? It's an element for sure. It has to be here. So basically what we're saying is in here, some of these elements are molecular in nature because they go around in pairs.
okay. So that's the bottom line that they got it.
Okay, very good. Very good. All right. So, let's see. I think this is a good place to stop for today. All right. We learned a lot, and hopefully when we start up again, we'll be able to pick it up and understand and learn new things. Okay?